scream a little bit more. Okay, so first of all, thank to the organizer for this very nice event and for giving me opportunity to give a talk here. And so the aim of the talk today is to show you a novel. This word already became associated to this workshop. A novel proof of equivalence of several definitions of Sobolev space in metric measure spaces. So we all know that there are definitions by approximation, by using Lipschitz functions, or for instance, by checking behavior along curves, or one definition that is maybe less known and less used up to now is that by the integration by parts. So this will be somehow the first topic that I will discuss. And the proof that I'm going to present will be based on smooth analysis. So we are going to reduce this problem on metric measure spaces to a question in Banach spaces. And there we are going to use a class of smooth functions called cylindrical functions that you might have seen in the talk by Savaret. And there we are going to apply some classical techniques in convex analysis combined with the superposition principle for normal one currents. Okay. And we will see, going through the proof or through the idea of the proof of this result, that it hides somehow a general principle and which is somehow a relation between plans that you use in order to test behavior along curves and the derivations which are used in order to give a definition by integration by parts and their mutual relation via normal one currents. Okay, so let's start. Okay, so the talk is based, this first part of the talk is based on the paper in collaboration with Enrico Pasqualetto, while the second topic is mainly contained in these two papers, of which one of them is already online, and the other one will be soon, I hope, in collaboration with Luigi Ambrosio, Toni Ikonen, and Enrico Pasqualetto again. So I'm going to fix a metric measure space where XD is a complete and separable metric space, while mu is a non-negative boundedly finite Borel measure on X. And just a couple of words of notation. So for given any Lipschitz function, I'm going to denote by lip A its asymptotic slope, which is a limit as r goes to 0 of the Lipschitz constant of f when restricted to a ball at the point x of radius r. And okay, we are also going to use this notation E plus and E minus for the evaluation map at start and the end and the starting time for any curve, Lipschitz curve, gamma parameterized in 0, 1. And by a plan on X, I mean finite Borel non-negative measure concentrated on the Lipschitz curves parameterized on point 0, 1. And I'm going to use this notation for the boundary of phi, which is just the difference between these two measures of push forward with respect to the evaluation map and the end. Okay, good. So first definition that I'm going to recall is one inspired by the notion via relaxation or approximation, which has been firstly considered by Shiger and later revisited by Ambrosio, Gilli, and Savaret. And so for this equivalence, we are going to show the equivalence in the case in which p is greater than 1. So for the moment and later, if there is some time, I will, or along the talk, I will comment also on the case p equal 1. Okay. So for now, let us fix conjugate exponent p and q, which are between 1 and infinity, 1 and infinity excluded. And for given any subalgebra of bounded Lipschitz function on X, which is contained and dense in the space of LP functions, I'm going to define this functional that you might expect that it is only this integral correctly scaled of the asymptotic Lipschitz constant of a Lipschitz function to the power p. But I'm taking this infimum among all the representative of a given function f in LP, which are in my algebra. Simply because if measure is not fully supported, then this wouldn't be defined well as a function on LP. Because if the measure, for instance, is a Dirac delta, then you might vary Lipschitz function for any given block, and it gives in the same equivalence class. So, and then you define Cheeger energy with respect to this chosen algebra as a weak lower semi-continuous envelope of the functional Fa. And the Sobolev space then becomes nothing but the domain of finiteness. And one can show that this Cheeger energy functional has an integral representation, and this integrand here, we are going to denote it df with respect to A, is called minimal A relaxed slope of our Sobolev function f. And when the algebra is the one that we usually take, that of Lipschitz boundary supported Lipschitz functions, I'm just going to write H1P and Pf without this subscript A. Then the second definition we have is that by looking at the behavior of function along curves, and roughly one says that f in LP is Sobolev if this weak upper gradient inequality holds along almost every curve for some function, non-negative LP function G. And now one can talk here about different notions of almost every. So you can have different ways of choosing curves that you want to look at. And today, I'm going to use a notion of non-parametric dynamical plans, which are introduced in the work by Savare after this work with together with Ambrosio and Di Marino, where these barycentric plans appear for the first time. And so I say that the plan, which I recall was a non-negative finite Borel measure on the space of Lipschitz. First, a plan is said to be non-parametric dynamical Q plan if it admits Q integrable barycenter, meaning that so this formula holds. So this is nothing but the integral of along gamma of your function f integrated in d pi, and it is equal as integrating f barycenter of pi in d mu for every boundedly supported Lipschitz function f. And then we are also going to ask that push forward along this evaluation map in the initial and the final time is absolutely continuous with respect to mu, and the density is in LQ. So I'm going to denote by this BQ of X the family of all such plans. And finally, to define the Sobolev space B1P, and B here stays just to remind about this Beppo-Levi property, so behavior along. And we say that F, LP function F, is in the Sobolev space B1P if there exists a non-negative function G in LP, so that this inequality is satisfied, and where this now is nothing but Fn gamma 1 times Fn gamma 0, and this one is right the very definition of barycenter. Okay. And mu almost everywhere minimal such function G is denoted by EF now B, and is called minimal weak upper gradient of F. And so the first topic, the first goal that I want to discuss here is the equivalence between H1P and B1P. And before going to the proof of this fact, let me just recall that when one is looking at behavior along curves, there is also a notion of Newtonian Sobolev space, which is very well studied by Mungalingham and also Finnish school and initiated by early works of Heinonen and Koskela, introducing the concept of weak upper gradients. And once you have, at least in the case p greater than 1, once you have this equivalence of h1p and b1p, then something that one can show just by looking to the negligible sets with respect to modulus and the negligible sets of curves with respect to plan, one can show that this space stays in between, so you get the equivalence between all of them. Okay, but let's now see how we can prove this theorem. And let's first I just comment, because this result is something which is already known. So what I'm going to discuss here today is a new way of proving this, but the fact itself is already known. And Ambrosio, Gilles, Savaret proved this equivalence using the metric flux semi-group. In their case, the notion of the space B1P was slightly different because they used test plans that maybe is something that are more used to see. And then Savaret proved the same equivalence using von Neumann min-max principle and representation formula for the dual Chigger energy, as you might have seen yesterday. And the proof of Savaret covers also the case of extended metric measure spaces, and I will comment on these extended settings. Then we have work by Eriksson-Bicken, who is proving the equivalence between H1P and N1P, so the Newtonian Sobolev space, and he has a different approximation. Okay. Then also there is work by Fornacier, Sodini, Savaret, and Sodini himself, which characterizes the algebras of Lipschitz functions for which it holds that those are the same. So not only for the Lipschitz one, but they characterize the algebras for which you can have this equality. And another comment, and this regards case, so this was all for the case p greater than 1, but regarding p equal to 1, Eriksson-Bicken, his approximation scheme works also in the case p equal 1. So he shows that h11 is equal to n11, but now you have this natural inclusion that I show you, that h is included in n, and then again n is included in b. But then this is again also, if you want to show the full equivalence, then you have to work on the equivalence between n and b direct. And this is what we do in this new preprint with Luigi Ambrosio, Toni Ikonen, and Enrico Pasqualetto. And while the techniques are above, and the technique that I'm going to show today, in the case p equal 1 are going to cover, it's not okay. They're going to cover BV functions. Okay. For this Ambrosio, Gilles, Savaret, it covers also the case of BV functions, and for the technique of Savaret and the technique that I'm going to show today, it's not written anywhere, but we think that it's going to cover BV. So, as I announced, this proof is going to use smooth analysis and is going to reduce a problem to the problem on when our metric measure space is actually a Banach space. So how to do this? So first of all, so let me do some reductions. So up to a localization argument, one can always assume that measure is finite. We restrict ourselves to a ball, and then we invade the space. Good. Then we can embed our complete separable metric space isometrically into a separable Banach space, and we can endow this Banach space with the push forward of our reference measure under such an embedding. And then we end up with a weighted Banach space, which is isomorphic to our original space, and something that, okay, this Sobolev space is on the Banach space and on the metric measure space will be the same, or there will be an isomorphism between Sobolev spaces. So you can look at, so you can assume that your underlying space is a separable Banach space. Okay, And something else that we can do to avoid this, defining this functional from the very beginning, this FA, by taking the infimum among all representatives. So we can always assume that the measure is fully supported. If not, then you can modify this measure by adding the sum of the Dirac deltas centered in some inner points which form a dense sequence outside of the support. And you can, in this way, obtain a metric measure space that will have the same Sobolev space as the original one, but now you have a fully supported measure. And so our assumptions are now that we have a separable Banach space with a finite measure and fully supported. And when measure is fully supported, then my functional f for all bounded Lipschitz functions is well defined just by taking this. Any questions so far? Okay, and under these assumptions, so now our goal is to show, so our goal, it would be enough to show that that H1P is equal to B1P, where we approximate by Lipschitz functions, but I'm going to show that even a little bit more so that you can approximate by cylindrical functions. Okay, and now, so cylindrical functions are a subalgebra of bounded Lipschitz functions on our Banach space, and they are functions which can be written as a composition of a smooth compactly supported function on some finite dimensional Banach space, and as P, you take any bounded linear operator. So as Giuseppe was showing yesterday, you can take finitely many elements of the dual space of your Banach space and then compose G with interpol. And okay, and so our main theorem. So if you show this for this smaller class, even better. So you can then deduce it for the class of Lipschitz functions, and in the end, by all this reduction coming back, you will deduce also our main theorem, the original metric measure space. And also this result, as you have seen yesterday, is already known, and Savare proved this also, and even in the extended metric measure space setting. But what is different is that his proof of this fact is using already a fact that you know that Lipschitz functions are dense in the Sobolev space on a metric measure space. Then when you take as a special case of your metric measure space a Banach space, then you can show that you can also approximate by cylindrical functions, so you can do better. So what I'm going to do here is that without knowing that Lipschitz functions are dense in a metric measure space, I'm going to show first that you can approximate on a Banach space by cylindrical functions, and then this will give you a result about the Lipschitz case. Okay. And just a word on notation. So for any cylindrical function f, I'm going to denote by dxf the Frechet, so the element of the dual of my Banach space, so the Frechet differential of f at x, meaning that you have approximation up to times. Okay, so proof of the main result goes like this. So one of the inclusions is usually always easy, and then you have this harder one. So here the easier one is the inclusion of H into B, and okay, so if you take your function f in H1P, then you have a sequence of cylindrical functions, so that asymptotic Lipschitz constant is converging to the minimal object f weakly in LP, and so that the functions themselves converge in LP to a function f. And then you can just start writing your weak upper gradient inequality that you would like to pass to a limit from the Lipschitz functions to that one. So you consider f in the partial phi, and this, given that I was assuming that this is in LQ and this converges weakly in LP, you can pass to the limit here, and then you can bound this difference of f in the gamma 1 and gamma 0 just by asymptotic Lipschitz constant of Fn in gamma t and the metric speed of gamma integrated with respect to dt. But now this, by the definition of barycenter, is nothing but here. And again, barycenter is in LQ, so you can pass also this to the limit and conclude that this upper gradient, weak upper gradient inequality holds with this df with respect to cylindrical functions. So in particular, the minimal weak upper gradient that we defined in the space P is less or equal to this one. Function is in B1P. So this is the easy one, just by the approximation. Now, in order to show the equivalence and the converse one, it is enough to show it in the integration. Okay. And the proof of this inequality is going to. So the idea is inspired by the work of Bushite, Butazzo, and Sepesher from 1997, where they used the same idea to prove the equivalence of the definitions of Sobolev space on the Euclidean space endowed with any Radon measure. So in order to go to the proof of this, let me just now again say that this differential of cylindrical functions induces a densely defined and unbounded operator from LP into the space of LP maps from B to the dual of B, and its domain is that of cylindrical functions. And then we can denote by D star its adjoint operator, which goes from the dual of this space to the dual of FP, which is okay. And now to proceed with the proof, we will need a technical lemma. And now this lemma already is suggesting somehow that we are going in the direction of the second topic of my talk, so to the derivations or vector fields, if you want, and currents. So given any element in the domain of this adjoint operator, for any element of the adjoint operator, there exists I in my class of plans, so that the boundary coincides. So is absolutely continuous with respect to mu, and this is the density is given by the star applied to S, and the barycenter. So the norm of the barycenter in LQ is less or equal than the operator norm of this of my L. Okay, and let us take this lemma for granted for the moment, and go to the inequality in the integral sense. So for brevity, I'm going to call this functional f with respect to algebra of cylindrical functions f cylindrical. And maybe I didn't mention, but for a cylindrical function, so that the norm of the differential at x of f is the same as the asymptotic Lipschitz constant of f functions. Okay, good. So we have this one. And now we are going to do some convex analysis. So we can consider potential conjugate of this functional, which is defined in LQ, and by definition it is just a supremum over all f in LP, and here you have the duality between f and g, and minus the functional, and then you take a supremum among all f. And now a classical result in convex analysis is telling you whenever you have a convex functional, and our functional is convex, then the lower semi-continuous envelope of this functional is nothing but the second conjugate of that. Okay, and so we are going to compute second conjugate. But in order to compute second conjugate, we first compute the first conjugate, and notice that our functional can be written as this composition of the LP norm and this linear operator, the differential. And then you can show, and maybe a good reference for this formula that I'm going to say is Castingal-Ladie. And it is saying that the potential conjugate of my functional is can be written as the infimum of the potential conjugate of the P norm applied to L, where L ranges in the domain of the adjoint operator, and the adjoint of L is nothing but for every G in L. And now the potential conjugate of the P norm is just the Q norm in the dual space, and then we get the potential conjugate of our functional looks like this. Now, if you think about case Rn, for instance, so if you have a differential, so what is the adjoint operator? It is the divergence. So what we are talking about here are vector fields with divergence. And now we are going finally to see what is the Cheeger energy. So I said the Cheeger energy is a lower semi-continuous envelope of my functional F cylindrical, and it is the second conjugate of that one. And now by definition, it is just a supremum over all G, the duality between F and G, minus the first conjugate. And the first conjugate we have just computed, and it was then by using our lemma, you can bound this above by these quantities, because for any L, there was a P in which we had opposite inequality, but here we have a minus in front of it. So you end up with this one. And then here, you can just put all of this into one supremum over all pi in your class of plans, and write it in this way, where this G d mu is just boundary of my pi. And then now I can use the fact that I'm taking F in P1P. So this is less or equal than the minimal upper gradient P1P. What is this? The name or the domain of which one? Domain of the adjoint. Well, so it's just the subspace here where this operator is well defined. So okay, or if you want, so this so d star of L is a function in LQ. So now if you test it against any function LP, it gives you L of the differential of L. Okay, so okay, we arrived here. And so what is my aim? So my aim is to show that this Cheeger energy is bounded by the P integral of this minimal upper gradient in B. And now once I am here, since my function is P1P, I arrived here. And here I just need to use Young inequality in order to bound above this product by the sum of LP norm. Minimal upper gradient plus the LQ norm correctly weighted, of course. And then this second summand is cancelling with this one, and you are left only with this LP norm to the power P weighted by 1 over P. And this is showing exactly the opposite inequality. So this main result in Banach spaces holds true if we assume that we have a lemma. So now what remains is to discuss lemma. And how much time do I have? Okay, so the proof of this lemma, so let me say this in words and not so precise, and then I will discuss it in more general setting. So the proof of lemma is based on the fact that any L in here induces a normal one current, so that the mass of the current is bounded above by this modulus of L times mu, and the boundary is the same as the adjoint applied to L. And don't worry, I didn't introduce currents yet. Raquel did some days ago, so that's good. But even if not, for the class of currents that I will need, you will see that we don't even need a definition, but we will just identify them with some other objects. Okay. And then once you have the cell that induces a current T, then by a superposition principle for normal one currents will give you a plan which satisfies this above. And actually superposition principle for normal one currents will give you even more that you need here. So we use this result, but we don't need it in too much. But nothing else to rely on. Okay, and so here I said that I would like to use only smooth analysis, and so I have to specify which normal one currents and which superposition principle we want to use. And you can directly, if you don't really want to insist on this smooth analysis, then you can use directly normal one currents in the sense of Ambrosio-Kirchheim and the superposition principle by Paolini-Stepanov and conclude. Otherwise, apart from embedding our metric measure space into a separable Banach space, you can also choose this Banach space to have a metric approximation property. And if you have a metric approximation property, then you can, so you have a sequence of bounded one Lipschitz operators with finite rank from the Banach space into itself. And then you can look at the image of this finite rank operator. And then this image is going to be a finite dimensional Banach space. So you can reduce your problem there, use their Smirnov superposition principle and the currents which are currents in the sense of Federer-Fleming, and then pass to the limit as this sequence is approximating every point in your Banach space. So this is what we do, but this is maybe more technical part of this. So this is how you prove this lemma, but now this lemma, if you now look at it in the level of metric measure spaces, it hides something else, and so let me now discuss this third notion of Sobolev space, which actually is this thing which stays in between. So we started from this relaxation type definition, then we ended up with this plan, but in between you had this L, which is in the domain of the adjoint. And what is this in general? So these are nothing but derivations in the sense of Di Marino, which was inspired by the work of Weaver, and introduced this integration by parts definition of Sobolev space. So what is a Lipschitz derivation in the sense of Di Marino? So it's a linear map going from boundedly supported Lipschitz functions into LQ, the Lipschitz Q derivation, if we have this weak locality property. And we have a Leibniz rule, okay? And the smallest g that you can choose up here in order to have this weak locality will be denoted by this modulus of B and called pointwise norm of B sometimes also. And by their Q, I'm going to denote the space of all Lipschitz Q derivations on X. Okay, and then for a derivation, we can introduce also a notion of divergence. And we say that P admits Q divergence if there exists, and when there exists, it's uniquely determined function div B in LQ, so that the integration by parts formula holds. Okay. Then how do we define Sobolev space? A function f in LP belongs to Sobolev space W1P if there is a linear map from the space of derivations, Q derivations with divergence in LQ into L1, so that there is, for some non-negative G in LP, you have this bound for every B derivation with divergence, and again, this integration by parts. Good. And also here, you can always define this new almost everywhere minimal object G, which I'm going to call dfW, which satisfies this above property. And so now in this forthcoming paper, and also in the paper which is already online with Ambrosio, Ikonen, Pasqualetto, we have studied the relation between derivations and plans through their mutual relation to normal one currents. And let me just show you a part of the results that one can have. And so let me assume here mu to be finite, now just for simplicity. And let us look at this class of normal one currents, and now we are on a metric space, so those are currents in the sense of Ambrosio. So I'm looking at normal one currents whose mass measure is absolutely continuous with respect to mu, and also the boundary is absolutely continuous with respect to mu, and have densities, both have densities in LQ. Now, how do you go from plans to, now we have plans, we have the plans with barycenter in LQ, we have derivations with Q divergence, and we have this normal one currents with densities in LQ. So now how we go from plans to derivations, given a plan in our class, it induces a derivation with divergence in LQ, just with this formula here. And actually you can show that for every pi, this modulus of B that is induced by pi is less or equal than the barycenter, and the divergence is minus the boundary of pi. And this map is actually surjective, and for any B you can find pi B so that actually you have an equality. So it's a submetry. Okay. And from derivations you can go to currents. Whenever you take a derivation with Q divergence, it induces a current in this class, just like this. Okay? So, and this map from B to TB is linear and bijective, and the mass is just this, and the boundary is minus the divergence of B. So if you want to think about current in this class, you can think about the derivation with the divergence. And then from currents to plans, as I already mentioned, so what Paolini-Stepanov says is that whenever you have a normal one current in here in particular, it induces a plan that will be here, which represents this current in the sense that this formula holds here, and the mass is nothing but the barycenter times mu and the boundary. Now if you go back to the lemma, so, and you take L here, then taking this L, you can induce a derivation from this L just by setting this for every cylindrical F, but not just by this, because in order to define a derivation, you should extend this definition to the space of boundedly supported Lipschitz. But I think this can be. And this, you can then show that this defines an element in LQQ, and the divergence of PL is minus adjoint of L. So in a sense, in this main theorem, putting this L in between, so what you end up showing actually is this H is equal to this space W, and W is equal to B. Relations that I just mentioned. Okay. How much time do I have? Is it a minute? Okay, I just have one more slide, just with a couple of comments about what is going on here. So what was the main thing in this argument that we have just discussed is that there is a linear differential on the cylindrical functions, and then we have computed this potential conjugate of functional here. But if you now forget about that you are interested in the density of Lipschitz functions or the density of smooth functions or whatever, but you are just interested to say that the Sobolev spaces defined in a different way are the same, then you can actually run the same argument using the abstract machinery of cotangent and tangent modules and the Sobolev differential, which are introduced by Nicola Gilli. So you can do the same argument with this linear operator here, and show this directly. So this becomes then, if you assume that you have at disposal this abstract machinery, then this proof of the equivalence of the spaces becomes really half a page. And In the case p equal 1, as I already mentioned, this presented proof should cover the case of PV functions. And, but anyway, the equivalence of all the notions that I mentioned is true also for one Sobolev functions. And this is what we have shown in this recent preprint. But in this case, you have to work on the modulus plan relation between, or the equivalence between these two. And in the future, somehow, we will also like to concentrate on the p equal infinity case and to see what happens. Then the last comment is about extended metric measure spaces and in the sense that Cabaret yesterday. So, and there is a work in progress by Enrico and his PhD student, Janne Taipalus, where they provide also in this setting this notion of Sobolev space via integration by parts and show via the same technique that we just have seen that this Sobolev space via integration by parts coincide with this one. So what's something that would be interesting to see is that if in this setting there is a notion of metric current and then to relate Planck's derivations and currents also in this setting.